Hello everyone, my name is Corbin Gustafson and this is my video submission for Experiment 5 XFLR. So the first thing that I did right here, you can see that I used the NACA 0012 and the NACA 4412 airfoil. You can import that geometry, but you can also go to foil, NACA foils, and then you can input whatever 4-digit code you want, so like 0012, and it would pop up right there depending on how many panels. For both of those, I believe I did 200. So it'd be just like that. But since I've already did it, I'm not going to do that again. To run analysis on your airfoils, you're going to want to go to Xfoil Direct Analysis. And here's the last thing that I did. So what you do is you have this airfoil right here, and you go to Batch Analysis. And this is less important for just like the airfoil cases, but when you go to get the wings, you're gonna want to run a lot of different at a lot of different radius numbers. So I went from 10,000 to 200,000, and when you run that, you're gonna get lots of polars like this. And what this does is it helps your wings converge on a solution. Because if you don't have that many runs for just the airfoil geometries, when you go to 3 dimensions, it just freaks out for whatever reason. So the next thing that you do after you run all of this is you go to wing and plane design. And here we are in wing and plane design. So the way you make the actual wings themselves is you want to go to define a new plane, and then I name it just like the name of the airfoils because the airfoil isn't changing. So I'll do like NACA 0012, and I'll call it the second one. Take away the fins in the elevator because we're just doing stuff on the airfoil. And then based on the specifications from the lab, I believe, let's see if I have my paper. All right, so I have it written down right here. So first we'll do the chord length. That was 10 centimeters, no offset. And then the span was 15.1 centimeters. So that would be half because it goes from the midline. So that would be 0.0755. Now to view the wings, you're just going to go over here and you can see that this is the cambered airfoil, the NECA 4412, and then the symmetric airfoil. All right. Now to run analysis on this, you're going to want to define the analysis. You can specify your velocity, which gives you a radius number. And you're going to do fixed speed, LLT, because if you do the horseshoe vortex, it does allow your solutions to converge, but it does not take into account the radius number. So if you have multiple airfoils running at different radius numbers, for certain aspects, you're going to get the same thing. So while LLT, the lifting line theory, might be a little bit more difficult to converge with, it's better for, or it's the only one that you can use for this project. So go ahead and save that. So now we have one right there. If you define another at the 60 hertz velocity, you can see the radius number changed. It's about double. So now you have these two right here. I'll try to run it for just one. Oh yeah, and the solution's unconverged, obviously. And I mean, there's no good way to go about doing this other than just trial and error. Sometimes it crashes, like I think it's about to do now. Yeah, so it crashed. Um, happens sometimes, happens to the best of them. So I'm gonna go ahead and define this analysis again. Um, Try to go from -8 to 24 in the steps of 2. The solutions did not converge, but no worries. I'm not gonna try to get it to make it converge in this video because it's actually magic. But what I can show you, all right, so this is the MATLAB code for this project. So the things that we were asked to find specifically for part 2 was the CL over angle of attack graph, the CD over angle of attack graph, the CL over CD over angle of attack graph, and the CL over CD graph. And so the way I went about doing that was, so right here I have the NACA 0012 wing 1. So that's made up of a cell right here. And inside of this specific cell is this vector that represents CL, or sorry, this vector that represents CL, and this vector representing CD, and this vector representing angle of attack. And so that's wing 1, wing 2, airfoil 1, airfoil 2, and then these are for the NACA 4412, so wing 1, wing 2, A1, and airfoil 2. So I put all those in there, and then you also, there were a couple other things later down the line that were mentioned in the handout. You know, lift curve slope average, all these things, but the video is only supposed to cover the first two. So we get down to this data analysis section, and this goes over how to do some of those other things. But we need to get to the plots. Okay. So how I did it was we basically take, for instance, this represents, the third cell represents angle of attack. So angle of attack on the Y and the coefficient of lift on the X. Or, I'm sorry, other way around. This is Y, this is X. And, you know, it's easier if I just show. Turn on local plots and run that. Okay. So CL on the Y, angle of attack on the left, over all the different wings at the different Reynolds numbers, which are here represented by the velocities. But that's all. That's right there. And then right here is the coefficient of drag over the angle of attack graph, the coefficient of lift over the coefficient of drag over the angle of attack graph. And right here we have the coefficient of lift over the coefficient of drag. And that's really all that that part 2 was about. You should definitely, if Damien's watching this, you should definitely give us a good grade because, as you can see, this took a hot second. But that's all I got for now, and thank you very much, and goodbye.